Hello everyone. This is another example of a circuit, basically a regulator circuit. And in this one we are trying to figure out what is the range of currents that we can draw from this regulator safely, considering that there is a maximum power that you can actually consume in the Zener diode. And usually this maximum rated power comes from the size of the Zener diode. There's a certain amount of power that you can consume in a component before it actually heats up to an extent that can damage the component. And usually that's size limited, and how the heat actually gets dissipated in the Zener diode, or whether or not the diode is connected to a heat sink properly so that the heat can be dissipated. So in any case, in this problem, that limit is 4 watts, and we would like to know what happens basically with what's the range of the current that we can get in the output. And there are certain values that are given. We know that the Ri is actually 150 ohm, and the input is 60 volts. Vz naught, which is basically the breakdown voltage of the Zener diode, is 15.4 volts. And the question is assuming that also Rz is equal to 0, which basically tells you that we are using an ideal model for the Zener diode. In other words, when the breakdown happens, the voltage, the Zener diode turns into a constant voltage. So as long as we assume that this actually is correct, then I can replace the Zener diode with an equivalent voltage source. And that the condition for that would be to make sure that there is at least 15 milliamp of current passing through the Zener diode. So with that condition, I can replace the Zener diode with the power supply model. So, and that's what I'm going to do. I'm going to take that, remove it, and put back in the model. Now the complete model would have been a voltage source in series with the Rz, the resistance, but the problem is making it easier on us, and assumes that the resistance value Rz that we would have put here if it wasn't 0 is actually 0, so we just turn it into a short circuit, and therefore we have a 15.4 volt right there. Now keep in mind, again, the condition for this happen is that there has to be at least a current equal to 15 milliamp passing through this node right here. Okay, so with that we're going to start our analysis. Let's start. Like always, we're going to label the nodes. So let's say that's our ground. This turns into Vi, which is 60, and this obviously turns into 15.4. Since this is a source, the equation for the source basically enforces that node to be 15.4 volt. Keep in mind, I could have labeled that as a different voltage and then come back and write the equation for this source nevertheless. So I'm going to call this I1, and I'm going to call this one IL, or II and IL, and this current is IZ, and there's a condition on that. We have to make sure that IZ is not less than 15.4. I'm sorry, not less than 15 milliamp. But there's actually a condition on how high the current could be too, and that's the first thing that we need to realize in order to understand what the range of IL would be, and that comes from the maximum power. So power that is consumed in this Zener diode is basically the current multiplied by the voltage. So PZ is equal to the voltage, which is constant as long as it's on, 15.4 times IZ, and this has to always be less than 4 watts. Right? So from this I can actually now calculate IZ. So IZ has to be less than 4 watts divided by 15.4, which if I remember correctly, this gives you about 260 milliamp of current. So this is actually the maximum current that you can draw, maximum current that you can pass through the Zener diode. And the minimum we already know is 15. So this is the range of current that is allowed. And based on that, we have to figure out what the range of IL is. So let's start doing the analysis again. KCL. So KCL tells you that II is equal to IZ plus IL. And then equations for components. So II is equal to 60 minus 15.4 divided by 150. And if I'm not mistaken, that turns out to be about 290 milliamp. I can do a quick calculation here with you. So it would be 60 minus 15.4 divided by 150. Yeah, it's 297. So 297 milliamp. And for IL, the equation is 15.4 divided by RL. And this equation that we have here is also needs to be taken care of. We have to meet that. And then the equation for the Zener diode, we already used it to assume that that's 15.4. So I think everything else is pretty much set here. I just have to set the two end values here. So one time I'm going to assume IL is equal to 15 milliamp and then calculate the RL from that. And then the other time I'm going to assume, which is this is IL min, sorry, it's not IL. So I'm going to assume that Z is 15 milliamp, from which you can then calculate IL. So IL would be II minus, so from this you know IL is II minus IZ. So this would be 297 minus, now IZ is 15. And off of that you can calculate your RL. And then the other time I can assume IZ, so this is IZ min, then with IZ max being 260, and again IL would be 297 minus 260, and I can calculate RL. So this one from here, this is the largest value, so this would be RL max, and this would be RL min. So you can calculate the range of the resistances using these two equations. So again, you can see that we decide what the model for our components is. In other words, we decide what equation for the components we have to use, and then we go back to the normal algorithm. Now this problem is different in the sense that what is known and what's unknown is switched. We don't know all the value for the components. Instead, we have limits on the currents and voltages, or mostly the current in the circuit, but nevertheless the process stays the same, and what's known and what's unknown is switched. Hopefully this has been helpful. Thank you for your attention.